Thanks, Greg, for telling me that the lecture is over. We can all go now and have 1 hour back. Okay, thanks so much for having me again here. And thanks again for putting me after an amazing lecture. Yesterday, you put me after Mike's lecture, today after Greg's. So I think Sandeep and Vivek and Praneeth really like me. So this in this talk, I will discuss this sort of very interesting and exciting direction of extreme simplicity bias that we observe in deep learning, what its implications are, and a few sort of things we have been able to solve, or a few problems that we are able to solve by using this particular lens. So this work is I'm very proud of this work, primarily because I did not do most of the work here. The work was mainly driven by 3 of our pre-docs or research fellows, basically folks that just finished their undergrad and they spent a year or 2 with us and led most of this line of work. So in particular, this work was started by Harshey, who has now moved to MIT for his grad studies. Then it was continued by Deepen, who moved to Harvard for his PhD. And then a significant part of it around out-of-domain distribution robustness was led by Anshul, who is now moving to University of Washington for his PhD. Another interesting thing is that last time Sandeep and Praneeth organized such a workshop, I gave a very similar talk. And at that point of time, we were able to pick a very good collaborator, Jatin, who is also in the audience. So I hope this tradition continues. There are many, many very important sort of interesting problems to be solved here. So if you're interested in any of these ideas, definitely feel free to contact us. Also, a big chunk of this work was done in collaboration with Shravanti, Venkatesh, and Aditi. And Praneeth, as usual, provides amazing technical leadership. So with these introduction, let's now move to what we mean by simplicity bias. So deep learning, as we know, has been super successful. It is all the rage. And benchmark after benchmark, it is showing that it can provide superhuman level of accuracy, right? So on ImageNet, it is it is known to be more accurate than humans. Same with speech recognition, machine translation. So it's doing really well. But at the same time, what people have observed is that when it fails, it can fail very, very poorly, right? So even if there's slight bit of distribution shift, the model stops working completely. So let's say if you trained your model on some images from real world about, let's say, cattle and glasses and whatnot, and then you give a little bit more stylized image to it, or say sketch of the image to it. Generally, you would expect at least humans to sort of understand that and do recognition properly, but these deep learning models can completely fail. The accuracies might drop from 90% to all the way to 10-20%. Then another big issue is this issue of adversarial attack. That is, if you take, let's say, an image, initially, you were able to detect the stop sign properly, but you had a little bit of some, put a few pixels. Many times, this perturbation might not be even visible to naked eye. And even then, the proper the deep learning system might start to sort of say a stop sign to be a ball or whatever you want it to say, right? And one sort of big risk that come with these models is that many times they can amplify the bias in the data set itself. That is, sure, your data set might have some bias for certain specific subcategories of population, but these deep learning systems are known to increase that bias, right? So one question is why all that is happening, why these neural networks are so brittle, and can we sort of figure out some particular spots where they tend to be really, really brittle. And for that, let's start with a very simple thought experiment. So suppose you have to distinguish these swans versus bears, right? When you look at these images, what all you are looking before you're saying that, oh, this belongs to a swan and here there's a bear here in this, right? Well, generally you will look this is our guess, our brain sort of processes a bunch of features that are available in these images. So you might be looking at color or background or shape or organs. So we are looking at these images holistically. So even if, say, there is a red duck, we will say that, sure, the color is weird, but we know the shape of this duck, and that's why we'll be able to maybe guess it, right? And similarly, you might have, say, a polar bear, And just by looking, like, while the resolution of the image might be very bad, just by looking at the background, you might be able to say that I'm not sure if this is bear or tiger, but like, because it is in this particular background, this must be a bear. So we are looking at all these features to sort of understand how to understand, like, the scene, or to understand a data point. The question is, does neural network also look at all the features that are available? And whatever limited information we have, it seems like that many times neural networks do not look at all the features that are there. So one of the very sort of famous examples around this is that of texture bias that was proposed by Gerhos in 2018. So they said that, okay, suppose I have, like, a model trained on ImageNet, performing really, really well, really accurate model, right? And you show this very small portion of this image to this model. It is able to identify that, oh, this texture belongs to Indian elephant, and it is, like, very, very high accuracy, or with very high confidence, it is able to predict that it is image of an elephant. Similarly, if you show an image of cat, it is able to sort of say that, yeah, this is a cat. It's very confident, right? But now, suppose if you transfer this texture of elephant to the cat, then what you see is that the neural network model is identifying this cat as an Indian elephant, and cat is not even there in top 3. So this clearly indicates that the network is extremely biased towards texture, and it is ignoring the shape feature. Whereas when you look at it, you'll say, sure, it has some sort of texture of elephant, but I also know that this is shape of a cat, and that's why it's a cat. Neural network is not able to do that at all, right? There are multiple other examples. So, for example, so there's a very popular data set called Waterbird Landbird, where you can have, say, certain type of birds in front of water background. That is what you typically see, and similarly certain kind of birds in front of land. And again, when you switch the background, all of a sudden you'll see that the model is predicting completely incorrectly, and people have been able to even attribute that, right? So there is some technique called GradCam, which is not completely accurate, but is able to sort of give some sense of where neural network is looking when it is making a prediction. And what it finds is that many times, like, the neural network is looking at the background more than the actual foreground. So for example, here it is looking at the background of this bird rather than. Okay. So it seems like neural network might, so far at least, might not be thinking or processing data the way we want it to be. That is, it is not looking at all the features that are there in the system. So the next sort of natural question is, why neural network is looking at only some of these features, and what type of features does it really learn or look at, and why it is ignoring some other features, right? And that is, like, the main sort of contribution or lens that we provide in this work. We are saying that neural networks, so we have this hypothesis, like, we don't have a formal proof in very general setting. There are some special settings where we do prove out this claim. But in general, our hypothesis is that neural network learns the simplest features it can to solve the, let's say, the given supervised learning problem or the given classification problem, right? So you might say that, okay, that's fine, but what do you mean by simple feature, right? Like, what is the notion of simple feature? I'll try to make this notion of simplicity a little bit more clear in a couple of slides. But for now, let's think that a feature is simple if it can be captured by a very, very simple neural network. Like, let's say if there's a feature which can be captured by a linear model, that's good. If there is a feature which requires, let's say, a one hidden layer neural network, it is a little bit more complicated. If a network requires very high width one layer neural network, or, like, multiple layer neural networks, then that features is even more complicated. So that's one mental model we can have, right? And based on that, now we can, like, the hypothesis is that simple features are selected by the neural network, and complicated features are ignored by them, right? So let's sort of look at this example to better understand this claim. So suppose we have two-dimensional data points. This is feature 1, this is feature 2, and we have two types of points, these blue points and red points. So these points we give as, like, supervised learning problem to the neural network, and we, like, give it all the power to learn, right? So we, let's say, train a one hidden layer neural network. So this one hidden layer neural network has power to learn whatever boundaries it wants to learn, right? Now, I mean, it's written on the slide, but it's still like, any guess what boundary this neural network learns? Like, so it can learn multiple boundaries. It can sort of use this boundary to separate these points. It can learn this boundary. It can learn this curvy boundary, whatever it wants, it can learn. Any guess on what it learns? Yeah, I think this is the last day, so people are somewhat tired, but it's written on the slide. Basically, what we find again and again is that neural network learns this simplest linear boundary, and it ignores the slightly more complicated boundaries. Right? So you can say that, okay, that's good. In fact, the simplicity bias of neural network, or this inductive bias of neural network to go towards simple solution, is actually touted as one of the reasons why these networks generalize so well. That is, while they might have all the capacity in the world, your learning theory people will say that this neural network can never be trained to have good validation loss because it will overfit so badly. Still, we observe again and again in practice that they actually generalize very well. So what is, so that's, I mean, that's a good sort of validation here. Right? That's fine. But if you think about it, like, in this case, this neural network is also sort of fundamentally violating the another thing that we tend to associate with our learning algorithm, which is notion of maximizing margin and reducing risk, right? That is, here, if you learn is this linear boundary, it might be very, very close to these features. Whereas there is this slightly more complicated boundary. It's not like it is using like, much more complicated function, but neural network is completely ignoring this more complicated boundary, which might have much better margin. Right? So loss function doesn't fix it at all. We can try hinge loss and whatnot. Doesn't help much. So the thing is that that is hard to control because neural network has some of this freedom in the parameters, right? So it can sort of scale the parameters to like, make it appear to you that, oh, it is maximizing the margin, but in reality it's not doing much. So there's this norm of parameters that come in, and that is actually hitting at the problem I feel at the heart, which is the type of regularizations that we do currently, they are not well suited to avoid this phenomena. So we need to come up with maybe better set of regularizations of our network to help. But yeah, so this, like, hyperplane has in some sense more risk, because if you perturb these points a little bit, your points will switch the boundary and it will lead to much worse accuracy. Whereas if you were learning this slightly more complicated boundary, you will not have that risk. So while you might be increasing your overfitting chances a little bit more, but you're providing me much more sort of, risk awareness, and it might be much more useful in practice. Right? At the very least, you should give me a knob to control such a thing in the neural network. But currently, that does not exist. So currently, based on whatever methods we could try, so we could try increasing the width of this network, changing the initialization, increasing the height of the neural network, changing the algorithm itself, changing the regularization parameters. None of that mattered. We almost always ended up this linear boundary only. Right? And at least in some simple settings, we do have, or in sort of relatively standard settings, we do have a fairly sort of, clean proof of why this happens, at least for this particular problem. So, so the claim is the following. Suppose you have, like, this problem, like, you have feature phi1, you have feature phi2, which has this sort of structure of 5 slab. That is, this feature phi2, when you look at it, it has points either here or here or here or here or here. And red points, so blue points are separated from red points, but blue points are not all clustered together. Like, they have these 3 slabs, and red points have 2 slabs, right? Interspersed. So now what we do is we will take this feature phi2, which is more complicated, and we will just replicate it, let's say d minus 1 times. So d minus 1 times, we have this slightly more complicated feature, and 1 time I have this feature phi1. If we can do that, or another sort of simpler setting is where I have this pretty much this setting, but all the other features like, phi3 to phi d, all of them are purely random, like Gaussian random. So they do not provide any extra information, right? So in those settings, what we do is we say that, okay, we will try to learn this one hidden layer neural network. For simplicity, we have dropped this weight that you learn here, and we are just focusing on these WJs we learned here. We initialize it at least like, according to the standard initialization techniques. I'm not sure if this is mu parameter optimal according to Greg. And we are allowing like, large number of samples. So order D square samples are allowed. The number of nodes in the one layer neural network is also very large, which is over parameter setting. We have D square nodes, right? And after doing all that, what we can show is that the linear feature, this one single linear feature, its weight can be as large as 1 by root k. And any of these other nonlinear features, their weight will be smaller than 1 by root k, right? Where k is the number of neurons in your hidden unit. So this clearly says that these nonlinear features are order 1 by root d smaller than the linear feature, right? And that's why your boundary is pretty much aligned along this linear feature, and it almost completely ignores these other features. And why does this happen, like, intuitively at proof level? Well, what happens is that like when you initialize your neurons randomly, these neurons are all firing in like, their own way, right? So because of that, when you do gradient descent initially, the linear feature will have much easier time because it can, in some sense, align all the neurons in one direction, and the gradient becomes much, much larger for that linear feature compared to any of these other nonlinear features. So because of that, like, it is able to sort of quickly reduce your loss from that direction. And after, like, your loss is decreased, you don't have much of a wiggle room. Like, you are, after that, like, you're sure your nonlinear features can come into picture, but they are not going to learn much more from it. So here, like, this is all good, but I haven't defined this notion of simple, like, features and simplicity very well. So this we can make a little bit more concrete, although in the setting of one hidden layer neural network. So this was like, this formulation was led by Jatin and Deepen. So the idea is very simple. We say that, okay, suppose we have this input X, we pass it through one hidden layer neural network, and we get our logits, and we want to now learn this, right? So the key thing, which is this weight matrix here, which essentially dictates what type of features you are learning in this network, right? So the notion of simplicity bias here is that the weight of matrix W is small. That is, we say that a neural network has extreme simplicity bias if rank of matrix W is extremely small, right? Now, in general, like, exact rank might not be small, but what we observe is that like, so that's why, like, we relax that definition, and we say that we will, rather than looking at exact rank, we will look at effective rank, which is intuitively, like, in some sense, like, what is the entropy in the singular values of this matrix? That is what we define as the rank. Right? That is it that you have one very large singular value and everything is very small, or all the singular values are very close to each other? Right. So here again, in several settings, we are able to provide rigorous proof that yes, if your data satisfies some kind of data distributions, then in, like, both the NTK regime as well as, like, finite width regime, we are able to provide formal proof of this simplicity bias. That is, we can show that the weight matrix that you are learning has very small rank, right? One very sort of, concrete example here is this particular data set. So, so in this data set, suppose we have these two labels, +1, -1. The first feature that we have is basically the label itself with some margin gamma, right? If gamma is smaller, then that sort of, the norm of that vector becomes smaller. That's it. And xi is, so all the other features are basically, like, completely correlated to the label. That is, if it is 1, then it is +1 or -1. So it is like a 3 slab kind of situation. So either your points, like, according to this feature, either you have positives, or you have some negatives, or you have positives. So there are 3 slabs that you have here. And you have, like, D-1 features like this. So here, both the linear feature as well as all these other non-linear features, so to speak, all of them have the information of the actual label. You should be able to learn the label from any of them, any of the features, right? And what we observe is that as long as this gamma is greater than some fixed constant, which is independent of the dimensionality, the max margin classifier that you learn with this problem, right? That is, with this classification task, will always have rank 1, right? How do we define this max margin classifier? Talk to Linek, who is in audience, but it's a sort of very simple definition. So in some sense, what we are saying is that max margin classifier for this problem always aligns with this canonical basis vector E0, right? That is the only linear feature, right? So this is sort of a statement which is independent even of the training algorithm that you're using. Like, if you have an algorithm that converges to max margin classification, we are saying that you will have extreme simplicity bias. So that's why I was saying that the issue might be in the regularization that we are putting. That is, if we can put some proper regularization, maybe we can hope to do better. But at least for the current standard type of regularizations that we have, this algorithm doesn't, like, it will not give us, it's a system which does not have such extreme simplicity bias. Any questions so far? Okay, let's go. So, so far I have been talking about these, very sort of cooked up examples of some 3 slabs, 5 slabs, and all. Let's see if this issue persists even in sort of more realistic looking data sets. So here, it's hard to sort of show it for purely realistic data set because, there it's very hard to sort of even come up with this notion of simple feature, complicated feature, and distinguishing that very clearly. So that's why we have a data set which is basically a cooked up version of MNIST CIFAR. So what we do is we take, let's say, MNIST digits, we take CIFAR images, and we put them together to form a super image. Right. So here, what we did was we took class 0, like a DZ0, and we slapped it together with a image of cat. Similarly, we have in our training data, we have images where you have digit 1 concatenated with image of a dog, right? So I call these as class 0 images, these as class 1 images, and I feed it in and I train my favorite image classifier. So you can train whatever you want, you can train your LeNet model, ResNet model, DenseNet model, whatever you want, you can train them. And after that, so once you've trained, on test data, we can now do this swapping of features, right? That is, we can say that, okay, what if I concatenated 0 with a dog, right? So what will model output? Will model still say that it is a class 0 image, or will it say it is class 1 image? Because the dog, in these class 1 images, there are dog features. In class 0 images, you have these features from digit 0. Right? So, well, it turns out that the model almost always predicts in fact, in our experiments, 99.9% of the time, it was predicting it to be a class 0 image. That is, it was focusing in some sense only on digit 0, and it was completely ignoring the fact that there was a dog present in the image, right? Now here you can sort of make one more argument that, see, this is sort of a misspecified thing. Either this could be class 0 or it could be class 1. So maybe model should be at least, maybe will be more confused. So while it is giving me wrong prediction, but model will at least be confused. So it turns out that that also doesn't happen. That is, let's say these blue points are the confidence or the logit values that the model give for your original set of point, right? So let's say original point was a 0 concatenated with a cat. After that, what I did was I randomized that cat with either putting a dog or even a cat, right? And so we call that as CIFAR randomized. And what we observe is that the logit values did not even change, they did not budge at all. So that sort of says that model had exactly the same confidence, no matter what. And that sort of indicates that the model did not depend on these dog features at all. It mainly just classified this based on this MNIST bug, 0 versus 1. And why is that happening? Well, because this classifying 0 versus 1 is much simpler problem, right? You can have very simple linear classifier that does the job very well, whereas for these CIFAR images, a linear classifier gives horrible accuracy. So this clearly indicates that, okay, the model is going for simplest features, just ignores the more complicated features. Now you can say that, oh, what if I change things? What if I use some other network like MobileNet or DenseNet? DenseNet has much more power. Well, it turns out that nothing really matters. So on the standard task, your model is doing well, but as soon as your you randomize your, let's say, the MNIST digit itself, the accuracy of the model falls to 50%. So this says that model is not looking at what CFAR part is giving, it is just looking at the MNIST part and based on that making its prediction. And same thing happens in this other settings. You can also say that, oh, what if I use some different activation functions? Maybe your activation function in the network is an issue. And what we observe is doesn't matter, whatever activation function you use, the answer remains the same. You can say, oh, what if I used different type of optimizers, and we observe that the same thing happens. Like no matter what optimizer, at least like whatever we could use at that time, it didn't matter. Like the accuracy drops. And similarly with the initialization, we tried these multiple initializations, and the same issue persisted. And so this is sort of, it seems like, yeah, this simplicity bias is real. And in this particular case, we were able to measure it by hooking up this MNIST images with CFAR images. Now, on some of these, like, little bit more practical data sets like ImageNet and Waterbird, Landbird, we observe this simplicity bias, but in the form of that effective rank formulation that we have. It is what we observed was that, let's say on ImageNet, when we train our model, initially the rank of the model is very high, that the rank of the penultimate layer, like the feature vector, that rank is very high because it is random, right? But as you go along the iterations, that is, as the model is optimizing and it is going towards sort of in a low loss situation, what we observe is the rank of the matrix is decreasing drastically, right? And the same happens for this Waterbird, Landbird data set also. So this sort of indicates that, yeah, you don't even need to sort of cook up these data sets like this. Even in this sort of more standard practical-ish data sets, this issue of simplicity bias is happening. Right? So now the question is, why do we care? Like, why do we care about the simplicity bias when we are doing well on our in-domain performance? Maybe we are sort of, we are minimizing our loss function properly, and we are able to generalize reasonably well. So, well, it turns out that if your model has this extreme simplicity bias, it will have very poor adversarial robustness, right? That is, if you take this particular feature and just perturb it little bit, right? Your model, like the data point is not perturbed a lot, but its adversarial robustness is very, very poor, right? And this can also sort of up to some level explain this notion, this phenomena of universal adversarial perturbation. That is, people have shown that there are some perturbations of your data point which are so dangerous that no matter what network you have learned, or for all those networks, like, those perturbations can be really brutal. That is, the accuracy comes down significantly. And this can explain that, right? Because if your network has this extreme simplicity bias towards a certain type of feature, no matter what network you're using, you are learning those exact same simple features. And that's why if you go and perturb those simple features, you are in trouble. So it's not really a property of what type of network I'm training. It is more like more of a property of the general neural network's tendency to go towards a particular type of feature. Another issue is out of distribution robustness. That is, if your distribution change along this axis little bit, again your performance accuracy comes down. And in some cases where the amount of training data that you have is very small compared to the amount of amount of, let's say, dimensionality of the problem, or compared to the complexity of the problem. In those cases, we can show that actually your model might be overfitting in some sense with the simplicity bias, and can lead to poor in-domain performance also. Any questions so far? So how we can try to fix it? So there are multiple ideas to try to fix it. One very simple approach is to maybe think of some sort of ensembling method, right? You say that, okay, sure, my model, when I train, it goes towards the simple feature. But what if I train multiple models? Then maybe I will, at least one of the models, I will retrieve a little bit more complicated features. So at least in the type of techniques that we tried, this technique did not work. We did try, some of these techniques that tried to come up with the classifier which was somewhat orthogonal to the initial classifier that you learned. So let's say if I learned a classifier or I learned a feature, I'll say that I'll try to suppress that particular feature and I'll try to sort of promote other features. So you can try to ensemble like that. Even those techniques do not work. They work up to some limited extent in these smallish problems, but even for the problems like MNIST, CIFAR and all, those techniques did not work very well, because intuitively, like in those settings, you can come up with so many simple features that you will just keep on removing one simple feature after another without ever getting to the actual complicated feature. Another idea is to train the models using adversarial training, right? Because we are saying that, okay, we do have this adversarial training, the model is very, very close to some of these simple features. What if I perturb them a little bit, then maybe model will learn to ignore and do well, right? It turns out that adversarial training also is not helping here a lot. When we train our model with this adversarial training, either so we have to set some sort of width of adversarial training, right? That we will say that, okay, in this epsilon ball, if you perturb the model, how is your prediction should not change. So if this epsilon is extremely small, then you are not solving the simplicity bias problem. And if this epsilon becomes even moderately large, then what happens is that the network stops training properly and its accuracy generally goes down quite a bit. So in either case, we are not able to really get very highly accurate solution that has the simplicity bias under control. So these were the ideas that we tried. Any other ideas you can think of that might help? So in general, if you have any thoughts or any sort of ideas that you think might be able to help here, definitely feel free to reach out to us. We are extremely interested in collaborating. So so the bottom line, so far is that we really don't know how to fix this simplicity bias in general. I feel like it's still sort of a open problem, and I think it's quite an interesting problem. And as I mentioned earlier, the key issue is somehow around the regularization of your parameters. That is, currently we use the standard L2 regularization of all the parameters, and that might not be good. Like for max margin classifier, in some sense, you can show that it is going to promote sparse classifier, that is classifiers that are looking at only a few of the features. But if you can come up with some better regularizations, then we might be able to learn a classifier which is a little bit more dense. So yeah, again, if you have any thoughts around that, happy to talk. So here now what we did was we said that, okay, if general problem seems very hard, but what if we look at some specific problems? So let's say we look at this problem of out-of-domain generalization. In that case, can we use this lens of simplicity bias to address the problem up to some extent? And that is what we did here. So let me define the problem setting clearly. So here what we did was we had some trained data, right? So trained data was from bunch of domains. We did not know the domain name. So let's say we had images from real world images. We had some images from products. We had some images from, say, some artwork, right? And then our goal was to learn a classifier or a model that will then generalize to any test domain. So let's say your test domain is that of sketches. We want our model to generalize to that new test domain. Right? So here, a couple of things. So A, we don't have any access to the data from test domain, neither the supervised information or unsupervised information. That is, we do not have any unsupervised images from the test domain, and we do not have any supervised images for test domain. And similarly, we do not know the domain name in the trained data. That is, we do not know that, oh, these are product images and these are these are these art images and these are real world images. We don't have any information. We are just given a trained data and we are told learn a classifier which is robust enough to generalize to any test data. So for this, to solve this problem, we said that, okay, simplicity bias seems like a one big issue in this out of domain generalization. So let's sort of, study simplicity bias in these kind of problems and understand how we can try to fix it. So to do that, we sort of, took one very particular test data set to develop our intuition and build a method around it, which is what we call colored MNIST. Colored MNIST is very similar to MNIST CIFAR with slight tweak. So in colored MNIST, what happens is in training data, most of our images have so let's say it is just a binary classification problem, that is 0 versus 1. And most of the images had this property that if they are of digit 0, then the digit 0 was red. And if it was digit 1, then the digit 1 was yellow. For most of the images, not all. Right? There was a very high correlation between the color and the label itself. In that case, what we did was we did this very simple experiment where we learned a convolution network on top of it, and we tried to see that what type of features are learned finally by the network. There are some features that are learned by the network, and then we do the final classification to whether it is digit 0 or digit 1, right? So we try to see, okay, what type of features are being learned. So here what we observed was that the feature value of this penultimate layer, so there were about 32 penultimate features. And there what we observed was 26 of them correlated very, very highly with the color itself. And only about 4 correlated very highly with the shape, right? So this indicates a couple of things, which is that in the penultimate layer, you might have these simple features that are appearing quite a bit. That's one. Second thing is that like the complicated features are still coming in. Like, it's not like it is completely wiped out. So that's the second sort of information. And one can try to now sort of say that, okay, either I will try to improve how many features, how many complicated features I have in this final layer and try to learn from that. And then the second thing that I'll try to do is to say that I will try to suppress the simple features that are there in the final layer and try to see that the classifier that I'm learning on top of it does not rely on these simple features too much. So while my network might be learning these features, simple features, I want to sort of suppress them as much as possible. And this intuition very interestingly sort of holds for these pre-trained features also. So let's say for ImageNet or like in general for images, there are some many interesting pre-trained features that you can get, right? So those are trained with semi-supervised, self-supervised learning and whatnot. So we observe a similar thing even for those pre-trained features. There is a lot of these features are correlated with the simple features, but there are few features that are fairly correlated with the actual, like let's say harder shape features also. Right? So there is some hope there, but when you train your model on top of that, it is still sort of going towards the simple features only, ignores the complicated features, and it has extreme simplicity bias because of that. So why is that happening? Let's understand that bit better, right? Because if let's say we are saying that in this penultimate layer, we do have some shape features, why is model not giving weight to those shape features? And why is it just focusing on these simple features? So well, here, I mean, the issue is the number, right? That is, if some feature appears again and again, the max margin classifier that you learn for that layer very naturally gravitates toward that particular feature, right? That is, let's say we had this very simple sort of setting. These are like, this is a 2-dimensional data set. These are positive, negative point. These are positive points, and we learn a max margin classifier on top of it. We know that max margin classifier will look something like this. But now what we do is we take these this second feature, and we replicate that second feature 5 times, right? So we sort of increase the weight of the second feature much more than the first feature. And what we observe is the network completely gets biased towards that feature. That is, network says that, oh, if the points belong in this region, then they are all positives. The point belongs in this region, they are all negative. It doesn't matter what the second feature is saying, right? It gets much more biased towards that particular feature, right? And this is very easy to see, if you write a couple of lines of how max margin classifier should look, this is what you will easily get, right? And what our hypothesis is that is precisely what is happening in these cases. That is while our little bit more complicated features are present in this penultimate layer, these simpler features dominate that penultimate layer. There are so many number that the classifier that we learn on top of it will completely get biased towards those features, and that's why we are not able to do well. So this is also indicating this issue that, oh, even if we put these pre-trained features and we do all that work, that is not helping us, because the final classifier that we are learning is very easily getting biased towards the simple features because of their numbers. So one sort of way to fix this is what we call feature reconstruction regularizer. So the idea is extremely simple. So that, okay, let's say this is the feature layer that we get, penultimate features that we have. We will take that, And we'll try to, from the logits that we get, and from that we get these logits to get the final prediction, right? So from these logits, we will try to predict this penultimate layer. That is, we'll say that from the logits that we are getting here, which are W transpose F theta X, we'll try to predict back the original features that we had. So why does it work intuitively? Well, intuitively, if the network ignores this little bit more complicated features and completely focuses on simple features, then the logits will not have any information about the more complicated features. The logits would have forgotten about it. So we are saying that no, we don't want to learn such logits. We want to learn logits which are able to reconstruct back the original set of features. Okay. Any questions about this? Yeah. So once we put this kind of thing, then what we observe is that even in this replication case, the final boundary that we are learning again goes back to the standard max margin boundary that we were hoping. So how does it work in practice? Well, in practice, we can show that on a variety of these data sets for OD generalization, this technique is able to help significantly over the baseline. So baseline is you don't worry about this OD issue at all. You just train your standard neural network to optimize the in-domain performance. And what we observe is that compared to that, if you just add this regularize at the end, you are able to get significant lift in accuracy. Any questions? Yeah. Mic. There is a mic. Okay.
Listen. Yeah. Could you please explain that feature replication once more?
Sure. You mean the regularization or?
Like when you did feature replication, you observed one result with respect to SVM in the previous case, in the previous slide.
Oh, yeah. So here what we did was we tried to mimic this setting, right? So here, in some sense, you can say that there are only two features. There is a color feature and there is a shape feature, right? And if you would have learned a maximum margin classifier on top of it, the picture might have been something like this. That is, there are these two features that are, let's say, separating the classes well, and I'm learning a good combination of them to solve the problem. But in practice, what's happening is that 26 features are correlated with color, right? So that is what we try to mimic here. We said that, okay, let's take this feature 2 and replicate it 5 times. So now the dimensionality of the data that I have is 6-dimensional. So rather than a 2-dimensional data set, I have a 6-dimensional data set. And when I learn a max margin classifier in that 6-dimensional space, the separating boundary that I get is this, not this, right? So this separating boundary is much more aligned with this feature that was replicated multiple times. And this regularization is geared towards fixing that issue. That is, we are saying that let's come up with a regularization so that even if there is a feature which is not appearing a lot, we want to give it some weightage. We want our logits to give it some weightage. So it's a very simple trick. But as I said, it works really well in practice. Sorry. Another sort of thing here is if you sort of use your model just by as we discussed in the penultimate layer, these color features which are simple dominate quite a bit, right? And these color features are because they are simple, they are also quite easy to perturb, right? That is, if you perturb them even with this 0.1, what we observe is that the accuracy of the model drops significantly. Like from 99%, it drops to 53%. Whereas if you perturb your shape features a little bit, the accuracy doesn't drop as much, right? So this sort of says that, oh, we should use then adversarial training for solving this problem because adversarial perturbation is dropping your accuracy significantly, right? The issue is that there are two things at play here. So if you do your full adversarial training, then a lot of people have shown that the performance or the accuracy of your overall network comes down. So while you might be more robust, but the overall performance, like even the in-domain performance of the model comes down. And again, there has been a fair bit of work which shows that in-domain accuracy is very highly correlated with the out-of-domain accuracy. That is, you cannot hope to train a model which is performing terribly for your training data, but it will perform very well on your out of domain distribution data. So that's sort of a general rule of thumb that people have developed, that if I want to fix OOD, I need to make sure that my in-domain accuracy is very good. And then maybe I add more robustness in some way to sort of perform better in out-of-domain settings, right? So if we do adversarial perturbation, like full adversarial training, this in-domain accuracy comes down so much that it doesn't help. And that is what we observe again and again. So the idea that we came up with is like extremely simple. We said that, okay, full adversarial training is bad. And we anyways know that I'm out of time. And we anyways know that our final layer, like the final penultimate layer, does have the little bit more complicated features also present. So why don't we just do adversarial training or fine tuning of the final layer, like where the final logic combination is happening, rather than the initial layers. And that is the idea behind this technique that we call DAFT. So in DAFT, there are two key ideas. One is we need we need to do adversarial fine tuning of the final layer, and the second thing is to make sure that there are enough important features or complicated features in the final layer. We try to distill it from a larger model. So what we observed was that generally large models tend to have many more interesting features in the final layer compared to a small model. So we said that we will then do a combination of these two ideas. That is, a distillation from large models to get more complicated features in, and then run adversarial fine tuning on top of that to make sure that we do not lose those interesting features or complicated features that we got in the final layer. So that is what DEF does. I will not go through those numbers. But one thing that I can sort of show is when we run DEF with this adversarial tuning, fine tuning and all, for this data set that we call colored fashion MNIST, which is very similar to the colored MNIST thing. That is, let's say you have either the shoes or the bags, and the background is quite correlated with the actual label. So here what we observed was that the DEFT model, like through adversarial fine tuning, was perturbing the color much more than the shape of the object. So that sort of indicates that, yeah, it was trying to, it realized that this feature is the one that is creating this this adversarial robustness issue, and that's why I tried to go and perturb it more and more to make sure that the model is more robust, right? And the bottom line is that from this technique, we were able to get significant gains. So this is the final accuracy on this domain bed, which is a combination of all these multiple OOD data sets that I showed. And what we observe is that the baseline model, like a simple ERM, gets about 63%. If we train it with DEFT, we get about 67%. If we train it with just FRR, we get 68%. And then we said that, oh, we have these two sort of complementary ideas. If we combine them, what we observe is we can get further 0.5% gain. So this sort of says that a combination of these ideas, which were developed with the simplicity bias lens, is able to give state-of-the-art accuracy on these out-of-domain generation of tasks. So that's sort of, it is a good positive thing to see. So let me conclude. So, as I said, our key hypothesis is that simplicity of bias of neural networks is extreme, and it can lead to significant brittleness. A lot of issues in neural network, at least we think, can be attributed back to simplicity bias. For fixing this simplicity bias, we will need to come up with maybe better regularization techniques or maybe better feature attribution techniques. And so far, by focusing on this out-of-domain generalization problem, we have been able to come up with these techniques like DEFT and FRR, which for certain benchmarks is able to provide state-of-the-art performance. And yeah, in future, we would like to sort of address this simplicity bias problem. That's all I have.